today we will be diving into the world of partial differential equations. In my opinion, some of the most beautiful equations that exist. And they basically model our universe. So if it's from drinking water, to listening to music, to turning on a light, or checking the stock market, every action can be described by a differential equation. And I think most people don't really realize how important they are. If it's in engineering or physics, they basically dictate how everything works. So this video's aim is going to be to try and show you how cool they are, how useful they are. So let's get started. So basically, we will start with ordinary differential equations, just because it's the foundation, and then we will explore more complicated partial differential equations, and we can also say that they are called PDEs, so it's going to be easier to call them PDEs. The first question you're probably asking is, why are they everywhere in nature? Why are they so important? So basically, the universe doesn't track where you are, it only enforces how you change. So if it's from dropping a ball on the ground or a train on a high-speed rail, what is always important is the rate of change, and that basically is the definition of a derivative. So an ODE is often a reverse engineering puzzle. You have the derivative, so the rate of change, and you want to find the initial function. Let's get started with an example. Let's say the derivative, so rate of change, is equal to a cosine. To solve this, we can just integrate both sides of the equation, and we find the family of solutions which is just a sine function. Don't forget the constant to englobe every solution because we don't know the initial condition. I'm not going to go too much in depth in the theory of ordinary differential equations, but I think it's important to see that they're also very useful and can have a lot of different forms. For example, the simple pendulum, a pretty well-known one, this models pure frictionless motion. Its solution gives us a perfect, never-ending wave. For the second one, we have a damped oscillator. By adding friction, the mass changes. The solution combines that wave with an exponential decay, showing exactly how a real pendulum slows down and stops. And for the third one, logistic growth, instead of population exploding further, this equation introduces an environmental limit. It's pretty famous in tracking animal population to viral trends. Now, it's time to have a look at partial differential equations. When looking into ODE'S, we notice that we only use one variable, which is often time. Space isn't taken into account. When introducing space, so adding x, y, and z coordinates, it becomes a PDE. We also use a change of notation from a straight to a curved D. We'll not be discussing too much about the solvability of PDEs, just because of how complicated most of them are. As you can see, an ODE requires 100 calculations, which is pretty straightforward, but when adding dimensions, it scales up a lot faster, so we often use constraints and conditions. Let's get started with a full-on example with heat transfer in a room. Firstly, let's assume that the whole room is heated at the same temperature by a machine. We can write the equation that describes the heat transfer with an ODE such that the variation of temperature is proportional to the difference of the interior temperature and the heated air. We can develop this expression and find the equation which describes the temperature in the room, and we can graph it out assuming that the heater is at 25 degrees and the initial temperature room is at 10 degrees. When going to infinity, we will reach the temperature of the heater, which is at 25 degrees. The only problem is that using an ODE for this problem is wrong and not rigorous, because every point in a room doesn't heat up at the same speed. The closer you are to the heater, the hotter it will get, which is pretty logical. We can now describe the heat transfer with a new equation that states the rate which the spot changes temperature over time is directly proportional to how different its temperature is from its immediate surroundings. To solve this PDE, we use a trick called separation of variables. We assume our temperature function can be cleanly split into a space part, phi of x, and the time part, g of t. By plugging this in, we can literally rip the equation in half. We are left with two completely separate ordinary differential equations, one for space and one for time. Let's first tackle the space equation. We know the ends of our rod are frozen at 0 degrees. If our constant lambda is 0 or negative, the math gives us a flat boring line, but if lambda is positive, we get a sine wave. These sine waves fit our frozen boundaries perfectly. but only at a very specific frequency called eigenvalues. Now, for the time equation, with our eigenvalues locked in, it's just a standard ODE. The solution is an exponential decay function, which models how the heat naturally dissipates and fades away as time ticks forward. Finally, we glue our separate parts back together. We multiply the spatial sine wave by the exponential time decay. Because our infinite wave, a wave can fit inside our boundaries, we actually get an infinite family of solution, completely solving our PDE. Now that we have finished analysing heat transfer for ODE'S and PDEs, we're going to go through Navier-Stokes and the Black-Scholes equations for both respectively water dynamics and markets. The top divergence equation represents the conservation of mass for an incompressible fluid. It states that the volume of fluid entering a space must equal the volume exiting. The second equation is an application of Newton's second law of motion, F equals m times a, to fluid dynamics. The left side represents the mass and acceleration of the fluid. The right side represents the sum of the forces acting upon it, internal pressure, viscosity, and gravity. The capital D represents the material derivative. It accounts for two types of change in a fluid: the local rate of change over time at a fixed point, and the convection rate of change as the fluid physically moves through space. The blue term is the pressure gradient. It dictates that fluid accelerates from regions of high pressure to regions of low pressure. For example, puncturing the pressurized balloon causes air to flow outward, strictly due to this pressure differential. The orange term accounts for viscosity, which measures the internal friction between adjacent layers of fluid in relative motion. The Navier square symbol is the Laplacian operator. It calculates how the fluid velocity diffuses over time, modeling the dissipative nature of viscous drag. The green term represents external body forces acting on the fluid. In most standard applications, this specifically accounts for gravitational acceleration. Finding a general three-dimensional analytic solution to the Navier-Stokes equations is currently impossible, functioning as an unsolved millennium prize problem. To find an analytic solution, we must apply strict physical constraints. Firstly, we assume steady flow, meaning conditions do not change over time. This eliminates the time derivative. Second, we assume straight, one-dimensional flow, which eliminates the convective acceleration term. Finally, we assume the pipe is horizontal, removing the gravitational force from the equation. By cancelling those terms, the complex partial differential equation collapses into a much simpler one. The remaining equation dictates that the pressure gradient moving the fluid forward is perfectly balanced by the viscous shear force pulling it back. Because this is a second order ODE, we integrate it twice with respect to the spatial variable. The resulting function reveals that the fluid's velocity forms an exact parabola. The velocity is strictly zero at the pipe balls, defined by radius r, and reaches its maximum speed at the exact center of the pipe. This graph shows the exact result of our math. The velocity profile of fluid flowing through a pipe. Notice the top and bottom edges. This is the no-slip condition. The fluid molecules touching the pipe wall are physically stuck to it, meaning their velocity is exactly zero. As you move away from the walls and towards the center, the friction drops. Each layer of fluid slides past the next one a little bit easier, allowing the speed to increase. This creates a perfect parabolic curve with the absolute fastest flow happening right in the center. We can't stop at fluid dynamics. Partial differential equations can explain so much more. And I think it would be pretty cool if we finish off with something that happens daily, so trading, and explaining how the stock market works. The Black-Scholes model looks scary, but we will try and understand it term by term. The first one represents time decay, known in finance as theta. This partial derivative isolates time to calculate the exact rate at which an option loses its value, simply because the expiration date is approaching. The second term calculates the underlying risk. The second derivative measures the acceleration of the option's value relative to the stock's current price, combined with the volatility variable, sigma, this term mathematically accounts for the random, unpredictable fluctuations of the stock market. The final terms introduce R, the risk-free interest rate. This ensures the equation respects the time value of money. It adjusts the option's final price to factor in the guaranteed returns an investor would have made if they simply left their capital in a zero-risk saving account. The ultimate mathematical plot twist is that the Black-Scholes model is not a completely new concept. Through a series of variable substitutions, this complex financial PDE perfectly collapses into the exact same one-dimensional heat equation that we looked at earlier. The mathematics are identical, but instead of modeling the physical diffusion of thermal energy through a metal rod, it models the statistical diffusion of financial risk and probability over time. I'm not going to go into any more details in the Black-Scholes, because it requires quite a bit more maths and I don't want to get too much into the theory. I think I've already done enough in this video to show you how important PDEs are. If it's from sound waves to quantum mechanics, to EM waves, or even to biology, they are everywhere. And if you just look outside of your window, you can easily find a PDE. I mean, we've done some interesting ones, but there's just so much more to do, and I just don't have time. But I wanted to thank you guys if you made it this far, it means a lot, and if you have any recommendations, I'm glad to hear them in the comments. Thank you guys, see you in the next video, bye bye!